So till now we have calculated electric field using Coulomb's law and Gauss law, and in these we have calculated field in certain symmetries only. But if you have any arbitrary charge distribution and you have to find potential and electric field, in that case we will use multipole expansion. So in multipole expansion we can find approximate V or E due to any arbitrary charge distribution at large distance. Large distance means point P is far away from the charge distribution. So you will get approximate V or E due to any arbitrary charge distribution at large distance from the source. So how to find? Let us consider you have an arbitrary charge distribution. Assume it's a arbitrary charge, and this is this origin O, and from this charge distribution at point P, that is r distance away from the origin, you have to find the potential and electric field. This is the arbitrary charge distribution, so you know its charge density rho, source charge, and you have to find potential and electric field at point P, and point P is far away from the charge distribution. So let us consider an elemental volume d tau dash. This is elemental volume, and this is its position vector is r dash. Let's take this position vector is r dash, and also assume this angle is theta dash. I have discussed that dash represents the source charge and this r vector represents the field point. So because it's a source charge, so its position vector I have represented by r dash, and this angle I have represented with theta dash. So you can find, let's take this distance is capital R. So first you have to find potential due to elemental charge and then integrate over this volume. So we have to find V as a function of r theta. We have to express in terms of r and theta. So that is given by 1 by 4 pi epsilon naught volume integral rho by mod r volume integral d tau dash. Let's take rho is function of r dash. So you have to find potential due to elemental charge and then integrate over the volume. But we have to express potential in terms of r and theta. So you have to replace 1 by r. We have to replace 1 by r in terms of r and theta. So I will not derive this expression, but if you write 1 by r, you will get different term in this expansion. So in multipole expansion, you have to remember those terms only. So let us see. This is given by 1 by 4 pi epsilon naught. We have to expand 1 by r in terms of r theta. So these terms are, first term is 1 by r volume integral rho r dash d tau dash plus you will get second term is 1 by r square volume integral r dash cos theta dash rho r dash d tau dash. This is the second term. Then you have third term 1 by r cube volume integral. This is r dash square by 2 3 cos square theta dash minus 1 rho r dash d tau dash and so on. You have infinite number of terms. In multipole expansion, you have to remember these terms only. You have to express 1 by r in terms of small r and theta. So you will get different term in the potential. So first term is potential is inversely proportional to r. Second term is potential is inversely proportional to r square. Third term is inversely proportional to r cube. So
सर ये कैसे लिखा लास्ट वन?
I have not derived it. You have to remember it. I told you in multipole expansion, you have to remember these terms if you expand 1 by r in terms of r and theta. So just remember it. No need to derive.
Sir, can you please show theta, which is the theta angle?
This angle between, I have represented in terms of theta dash. So this angle
Yes,
between
sir.
r and this is theta dash.
Sir, this is the same theta in the
Okay.
VR
Don't
theta.
confuse with this theta. We have to finally write in terms of r only. Let's see in terms of r. Don't confuse with theta. Let us write in terms of r only, in terms of distance only. Let us expand in terms of r only. We have to see dependence with r, and this angle is theta dash. Just to differentiate with source point, I have taken here dash. I told you what is the coordinate notation. Source is function of r dash and field point is function of r. Is it clear? So you will get infinite number of terms if you have any arbitrary charge distribution. And this first term represents the monopole, because you know in a discrete charge, if you have a single charge, potential is inversely proportional to r. So in multipole expansion, we have different terms. First term we'll call it as monopole. So let us represent monopole by single charge plus and also show the potential and electric field. So potential will be proportional to 1 by r and electric field is proportional to 1 by r square. If potential is proportional to inversely proportional to r, electric field will be proportional to 1 by r square. Second term is dipole term. So dipole, let us represent by plus minus. And you know in dipole, potential is proportional to 1 by r square. We have discussed dipole, potential due to monopole and dipole, you know. So electric field will be 1 by r cube. Next term is quadrupole. What is quadrupole? So in a quadrupole, you have 4 charge and these are plus minus plus minus. Charges are placed alternatively plus minus at the corners of a square. So this represents a quadrupole. And in quadrupole, if you see potential at large distance, you will see that is proportional to r cube, and then electric field is proportional to r power 4. In multipole expansion, you can calculate up to 3 terms only. That is the limitation of multipole expansion. You have other terms also. Next term will be octopole. At least remember up to octopole. In an octopole, you have a cube. charges are placed alternatively at the corners of a cube. We have discussed this example in case of electrostatic energy. So charges are placed at the corners of a cube. So let's say this is plus, minus, plus, minus, minus, plus, minus, plus. This represents an octopole. And in octopole, potential is R power 4, electric field is R power 5. And so on. You have infinite number of terms in multipole expansion. If you expand this term, you will get different terms. These are the different term and you know their dependence. So you have to remember these dependence. So in a given problem, when source charge is given, you have to calculate different terms. For example, when charge density is given, calculate this integral. If this integral is non-zero, if this first integral is non-zero, so potential has dependence on potential is 1 by r. Main dependence is 1 by r. And higher order terms will give you correction term. If first integral is 0, then you have to check for second integral. If second integral is non-zero, first is 0 and second is non-zero, then dependence is 1 by r square. And this is the correction term, first correction term. If this term is also 0, you have to check for third term. If this term is non-zero, dependence is 1 by r cube and higher order terms are correction term. So in multipole expansion, you have to calculate these terms that will decide the approximate dependence. So first non-zero term will give you approximate dependence. In this, you will see first non-zero term will give approximate dependence. And higher order terms are correction term. So you can easily write the approximate dependence and then you know you have correction term also. You have first correction term, second correction term and so on. In this, sometimes you have to find monopole moment and dipole moment of the charge configuration. So we will define monopole moment and dipole moment of the charge configuration. So what is the monopole moment? Let us see monopole moment. What is monopole moment? So monopole moment is total charge of the configuration. What is the total charge? So Q mono is given by, you can see this first integral is rho d tau. That represents the total charge of the configuration. So we can write this as volume integral rho r dash d tau dash. Q mono is the total charge of the configuration. This is in terms of volume charge. We can also define this for surface charge, line charge, as well as discrete charges also. So we can write for surface charge, this can be written as surface integral sigma r dash dA dash. For line charge, this can be written as line integral lambda r dash dl dash. We can also define for discrete charges. This is for continuous charges. And for discrete charges, Q mono is given by summation over I1 to N Qi. This is Ri dash. Q mono is Qi Ri dash, where Qi is the discrete charge at different location. And what is Ri dash? Ri dash is the position vector of source charge, position vector of source charge at ith location. Position vector of source charge at ith location. So if you know charge and their position vector, you will get monopole moment for discrete charges also. So if you calculate, if Q mono is non-zero, let's calculate Q mono, and if it is non-zero, so what will be a potential approximate dependence is given by 1 by 4 pi epsilon 0 Q mono by small r. This is the approximate dependence. Plus you have correction term. But you will get the approximate dependence. Whenever in any charge configuration Q mono is non-zero, potential is approximate dependence is proportional to 1 by r or inversely proportional to r. But if Q mono is 0, if Q mono is, because this will give, first term will give you approximate dependence, but you will get, if you calculate other terms, these are the correction term. For example, in this case, first correction term is the dipole term is the first correction term, quadrupole term is the second correction term, and so on. So because you have infinite number of terms and you will get only one non-zero term, so other terms are correction term. If Q mono is 0, then you have to check for second term, and for second term we can define the dipole moment of the charge configuration. So let us see how you will define dipole moment. So we know potential due to dipole. Let us use, we know that what is the potential due to dipole? V dipole is given by 1 by 4 pi epsilon 0 P dot r cap by r square, where P is the dipole moment. So from this expression, let us write the V dipole. This is V mono. So V dipole will give you second term. So you can write 1 by 4 pi epsilon 0, and let us see what will be from this relation. What will be r cap? What will be vector r cap dot vector r dash? Let's see, this is r cap and this is r dash. So what will be this dot product? This will be mod r cap mod r dash cos theta dash, or you can simply write this as r dash cos theta dash. You can see here r dash cos theta dash. So we can replace r dash cos theta dash by r cap dot position vector r dash. So you can write this as r cap by r square dot, this you can write volume integral position vector r dash rho r dash d tau dash. You can write in this form. R dash cos theta dash is replaced by r cap dot r dash, because r cap dot r dash is r dash cos theta dash. So if you compare with this relation, you can see this term will give you dipole moment P. This is the dipole moment P. So dipole moment P is given by volume integral r dash rho r dash. In this case, let us see, this Q monopole is, just make this correction. I have written here dipole moment. It's not a Q monopole. Just make this correction. Q mono is only total charge. I have written here dipole moment. Please correct it. I told you Q mono is total charge of the configuration. So that is simply sum of the charges. So please correct it. This is summation over Qi is the monopole moment. That is the total charge configuration. I have written here dipole moment. Is it clear? Please correct it. Q mono is simply sum of Qi, I1 to N. And this is the d tau dash. This is the dipole moment of the charge configuration. Similarly, we can write dipole moment for surface charge, line charge, as well as discrete charges. For surface charge, we can write this as P is R dash sigma R dash dA dash. We can also write dipole moment for line charges. This is R dash lambda R dash dl dash. And for discrete charges, dipole moment of the charge configuration is given by summation over I1 to N. This is the Ri dash. This is the dipole moment. So I have written dipole moment here. Ri dash, I have already discussed. Ri dash is position vector of source charge at ith location. This is Ri dash. If you have to find dipole moment, then you need Ri dash. In case of monopole moment, you have to just find total charge. So discrete charge, sum of the discrete charge, simply sum of Qi. But in dipole moment, you need Qi Ri dash. Ri dash is the position vector of source charge at ith location. So in this case, again, if dipole moment is non-zero, so V is proportional to R square. Approximate dependence is 1 by R square. And then other terms are correction term. If dipole moment is 0, then check for quadrupole. Check for quadrupole term. So in multipole expansion, you can check up to third term only. That is the limitation. You cannot go beyond the third term. So that is the limitation of multipole expansion. Is it clear? Now, let us note in this case, you will see if you have to find dipole moment, point number 1, if Q mono is 0 and P exists, means dipole moment exists, then P is independent of origin. We will verify this statement. Whenever Q mono is 0 and dipole moment exists, then it is independent of the origin. So in objective questions, if Q mono is 0, you know total charge is 0 and you have to find the dipole moment, then you can shift the origin according to your convenience so that you can easily find the dipole moment. So we will discuss this point. And if Q mono is non-zero, then P depends on origin. So you have to remember these points in multipole expansion. And you can also see that in the expansion, you have only specific term like monopole, dipole, quadrupole, octopole. So nature allows these symmetries only. If you have any arbitrary charge distribution, using superposition of these symmetries, you can have that charge distribution. For example, you don't have tripole, because tripole you can form using 3 monopole or 1 monopole and 1 dipole. You don't have pentapole. Pentapole you can have using monopole only, using monopole and dipole, or using monopole and quadrupole. So that's why in multipole expansion you are getting only these terms: monopole term, dipole term, quadrupole term, and so on. So using these terms, you can have potential or electric field of any arbitrary charge distribution, and you will get approximate V or E. Is it clear? So we will see example based on multipole expansion. You have to remember these points. So in today's class, I will discuss only for discrete charges, and in next class I will discuss examples based on continuous charge distribution. So let us see first example. Consider this case. This is X, this is Y, and this is Z, and charges are, this is minus 2Q, this is minus 2Q, you have 3Q, and this is Q. All are at a distance away, and this is the origin. This is first part. Then you have second part. In second part, this is X, Y, Z.
Minus. So it's minus 2Q on both the sides?
Minus 2Q on both sides. Next is on the origin you have minus Q charge, and this is 3Q. This will be A. And third case, this is second case, and you have a third case, X, Y, and Z. This is minus Q, and this is 3Q, A distance away. in these examples, you have to first find Q mono, then find dipole moment, and see approximate potential. Write down approximate V. In each case, you have to find Q mono, dipole moment, and the approximate potential. So in case 1, what will be Q mono? Minus 2Q minus 2Q plus 3Q plus Q. Sum of all charges, this will be 0. Then you have to see dipole moment. What will be dipole moment? Qi Ri dash. So start with this charge. What will be position vector? Minus 2Q Ay cap, then plus 3Q Az cap, then minus 2Q into minus Ay cap, then plus Q into minus Az cap. So what will be this value? So this will cancel out. Minus 2Q Ay cap plus 2Q Ay cap, and 3Qa minus this is 2Qa Z cap. This is the dipole moment. This is the dipole moment. So what will be potential? Potential will be 1 by 4 pi epsilon 0 P dot r cap by r square. So this will give you, this is the approximate dependence. So what will be, if you take dot product, z cap dot r cap is cos theta. So you can write this as 1 by 4 pi epsilon 0 2qa cos theta by r square. I have written this in spherical symmetry. Write down approximate V in spherical coordinate, in spherical polar coordinate. So z cap dot r cap is 2qa cos theta by r square. So that is the approximate potential in this case. Similarly, in second case, what will be Q mono? 2Q. 3Q minus Q, this is 2Q. So dipole moment minus Q into 0 because this is at the origin, and plus 3QA Z cap, 3QA Z cap. So dipole moment P is 3QA Z cap. And what will be potential? Approximately 1 by 4 pi epsilon naught. Again, P dot r cap is 3QA cos theta by r square. No, this is the potential due to dipole. In this case, approximate dependence is 1 by r. So you will get 1 by 4 pi epsilon naught Q mono. Q mono is 2Q by r. This is the approximate dependence. And you can also write first correction term. What will be first correction term? 1 by 4 pi epsilon naught 3QA cos theta by r square. So this is the first correction term. This is the approximate dependence because Q mono is non-zero. So approximate dependence is 1 by r. And dipole term will give you first correction term. In third case,
Sir, Q mono is 0, not equal to 0. In both cases, dipole moment is Qi into Ri dash. Same formula we will use.
dipole moment is always Qi Ri dash. But when Q mono will be 0, you will see it is independent of the origin. I will discuss that case. So Q mono is non-zero. Non-zero means approximate dependence will be 1 by r. So you can write first correction term also. But if you have to see dependence, in this case, 1 by r. Approximate dependence is, in this case, approximate dependence is 1 by r. I have written first correction term also. Again, in this case, Q mono is 2q. So what will be dipole moment? This is 0. So you will get 3qa y cap. So what will be potential? 1 by 4 pi epsilon naught 2q by r. This is the main dependence, 2q by r plus first correction term 1 by 4 pi epsilon naught p dot r cap. P dot r cap. So here you have y dot r cap. So what is y dot r cap? That is sine theta sine phi by small r square. Y dot r cap in spherical symmetry. So that will be sine theta sine phi. You know what is z dot r cap is cos theta. If you take projection in xy plane sine theta, so x dot r cap is sine theta cos phi, y dot r cap is sine theta sine phi. So I have written it in spherical symmetry. This is the first correction term. So you can easily find q mono, dipole moment and the approximate potential. So now we will see next example. Let us see in this case. We have 4 charges. This is plus q, minus q and minus q. This is in xy plane. And assume this is the origin. You have to find, let us find q mono dipole moment. In this case, find q mono dipole moment and also find this ratio. What will be VR by V2R? Potential, ratio of potential, and where R is far greater than A, means point R is far away from the charge distribution. So you have to find approximate dependence, then you can find this ratio. And their sides are, you know, their sides are A. This is A. So you can easily see q mono. What will be q mono in this case? 0 plus q minus q minus q. Q mono is 0. Now, if you want to find dipole moment, you must know position vector of each coordinate, each point. So this point is a by 2, a by 2. This is a by 2, a by 2. This point will be minus a by 2, a by 2. This point is minus a by 2, minus a by 2. Minus a by 2, minus a by 2. And this coordinate is a by 2, minus a by 2. So you know the position vector of each charge. So dipole moment is given by, start with this charge. So you have minus q, take a by 2 common. So this will give you x cap plus y cap. Then plus q charge, take a by 2 common. So this is minus x cap plus y cap. Then third charge, plus q, take a by 2 common. You have minus x cap minus y cap. And then minus q, a by 2, x cap minus of y cap. So let us see. This will be, this is minus y cap, this is plus y cap, minus y cap plus y cap. So these terms will cancel out. And what about x cap? Minus, 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 minus. So this will give you a by 2 is a, and you will get 2a. So finally you will get minus 2qa x cap. This is the dipole moment of the charge configuration. So dipole moment is non-zero. So what will be approximate dependence? This will tell you that V is proportional to 1 by R square. So we can write this ratio. This is 1 by R square and this will be 1 by 4R square. So this will give you, this ratio is 4 because dependence is 1 by R square. So this ratio will be 4. And if you have to find ratio of electric field at these 2 points, then this ratio will be R cube because V is proportional to R square. So E is proportional to R cube. In objective questions, in multipole expansion, always see whether you have to find potential or electric field, because potential is 1 by R square, then electric field will be 1 by R cube. So be attentive in multipole expansion example. Otherwise, there will be silly mistake. So you have to see whether it is potential or electric field. And this will be 1 by 8 R cube. So this ratio will be 8. So when potential ratio, you will get 4. Electric field at these 2 point ratio will be 8. Now we can verify another point that when Q mono is 0, dipole moment is independent of the origin. So let us check, because Q mono is 0. Now we can shift the origin according to our convenience. So let us use this trick. Shift the origin because Q mono is 0. So this is X and Y plane. Same charge. So now this is plus Q, this is plus Q, this is minus Q, and this is minus Q. Side is A. This is the origin. So what will start with this charge? Dipole moment is Q mono is 0. Same charge configuration. Q mono is 0. So in this case, you will get minus Q A x cap plus y cap, then plus Q A y cap plus Q into 0 and minus Q A into x cap. So you can see this y cap, this will cancel out and you will get minus Q A x cap minus Q A x cap minus 2Q A x cap. You will get same dipole moment here. So whenever Q mono is 0 and you have to find dipole moment, you can shift the origin according to your convenience. For example, in this case, you can easily find the dipole moment. Instead of calculating, in this case, you can simplify your calculation if you shift the origin at one particular charge. So you have to remember this point. Whenever Q mono is 0 and you have to find dipole moment, shift the origin according to your convenience. Is it clear? So now we will see another example. Let us see next example. In this example, you have considered same charge, but now they are, this is, let's say this is plus Q, minus Q, this is plus Q, this is minus Q. Again, consider this example. You have plus Q, minus Q, plus Q, minus Q, and you have to find what will be this ratio, ER by E2R, where R is far away from the charge distribution. Charges are plus Q, plus Q and minus Q. So in this case also, Q mono is 0. plus q minus q plus q minus q. So q mono is 0. Now see dipole moment. What will be dipole moment in this case? Start with minus q. So minus q a by 2 x cap plus y cap plus q a by 2 common minus x cap plus y cap, again minus q a by 2 minus x cap minus y cap, and plus q a by 2 x cap minus y cap. So you can see minus q x cap y cap, then plus q a by 2 minus x cap plus y cap, again minus q a by 2 minus x cap minus y cap, and this is plus q a by 2 x cap minus y cap. So just see, this is minus x cap minus x cap, so you have plus x cap and plus x cap, so x cap term will cancel out, and this is minus y cap plus y cap, again plus y cap minus y cap, so all will cancel out. So in this case dipole moment is 0. In this case dipole moment is also 0 because it's a quadrupole term. I have to retain that when charges are placed alternatively, that is the quadrupole. That's why you are getting dipole moment is 0. So it's a quadrupole. It's a quadrupole. And in quadrupole, potential is proportional to r cube. So electric field is proportional to r power 4. So what will be this ratio? 1 by r power 4 by 1 by 16 r power 4. So this ratio is 16. Is it clear? It's a quadrupole. So potential is proportional to 1 by r cube and electric field is proportional to 1 by r power 4. Is it clear?
Yes, sir.
Yes, sir.
Let us see next example. This is x, y plane. Now you have a equilateral triangle. This is an equilateral triangle. And charges are q, this is q, and this is minus 2q. And their sides are a. Find the dipole moment of the charge configuration. Let us find the dipole moment of charge configuration. This is the origin. So in this case, what will be monopole moment? Q mono, that is 0. 2q minus 2q, q mono is 0. So in this case also dipole moment will be independent of origin. So you can easily shift the origin. Let us see. This is the equilateral triangle. This is x, y. This charge is q. This is q. And this will be minus of 2q. Side is a. So this is also a. This will be a by 2. And this distance will be under root a square minus a square by 4. So that is under root 3 by 2a. This will be under root 3 by 2a. So you know position vector of each charge. This is 0, 0. This coordinate is a0, and this will be a by 2 under root 3 by 2a. So you can easily find the dipole moment. Start with this charge. So minus 2q, then take a by 2 common. So that is x cap plus root 3 y cap plus q into 0 and then q a x cap. So you can see this plus q x cap term will cancel out, and this dipole moment will give you minus under root 3. This 2 will also cancel out, minus root 3 q a y cap. In this case, this is the dipole moment. Because q mono is 0, so dipole moment will be independent of origin. Even if you calculate in this case also, you will get same dipole moment. So you have to remember this point. Whenever q mono is 0, dipole moment is independent of origin. So you have to remember these case.